C'est un grand plaisir de recevoir aujourd'hui Roch Glitho, professeur à Concordia, un ancien ami et collaborateur. Nous avons déjà obtenu ensemble plusieurs subventions. On travaille ensemble depuis une dizaine d'années, même plus peut-être. Roch, j'ai connu Roch quand il était chez Ericsson. Il a passé plusieurs années et ensuite il est devenu professeur à Concordia, à l'Institut CIISI. Le nom est toujours compliqué pour moi à retenir, mais qui est un département à Concordia. Et aujourd'hui, il détient une chaire de recherche industrielle avec Ericsson et encore 5G. La présentation va porter sur le in-network computing. Je vous laisse la parole, Roch.
Merci beaucoup. C'est un plaisir pour moi de faire la présentation ici aujourd'hui. La fois que je vais
OK.
Also, I will be talking of in-network computing for volumetric media delivery. I'll present the principles.
No, I am transferring the voice.
Okay, so I'll present the principles, then a very concrete case study, and then sketch the research directions at the end. Something is not working. This screen is holding.
OK. Your screen, right?
Yes, my screen is okay.
Now it's okay. Don't know what happened.
Okay, good. All right, so I will start by some selected references. If you wish to know about holographic communication, I would strongly recommend the first one because I will talk a lot about holographic communication. Then the second one is more on volumetric media delivery. Third one is about the so-called metaverse. I will just say a few words. And then the network computing. The third one is a short survey, I think, which really explains well what the network computing is about. And the case study will be based on a joint work done with UCAM in the context of the scoring project. In the IEEE Communication Magazine paper published this month. Okay. So let us start with holographic concepts. There are several holographic concepts today. It is actually becoming a fashion. Usually, we have virtual avatars which are projected on the stage, and this is synchronized with the music. The avatar might perform alone or might perform with a live band. It's important to say that avatar, audience, and live band, they are in the same room. So actually, there is no transportation of holograms. So that's the way it goes today. And there's no volumetric media delivery. Because I mean, to deliver volumetric media, you have to transfer hologram from point A to point B. And nevertheless, it seems to be quite interesting phenomena, as I will show here. There is currently on show in London. You may buy a ticket and go and see. There is the famous Swedish group, ABBA, is a group from the 70s, 80s. And avatars are currently performing in London. Okay, they are all in Sweden houses, but the avatars are on stage. So one point here is that it is a show which can go on 24 hours a day. It is in a specially designed concert room. The interesting point here is that the avatars show them when they were in the 20s. So it is the ABBA group from the 70s and 80s, although they are all now over 70. It seems to be a very successful show. Okay. Another example here, much earlier, 2012, and there's no transition between the musical style, because there we were talking of pop music, but here we are talking about rap. So you can see Snoop Dogg in a duo with Tupac. The thing here is that Tupac was dead, shot dead in 1996. Okay? And the show was in 2012. Another interesting point is that Tupac in his song was referring to events which have happened after his death. So these are just quite some illustrative examples. You have Whitney Houston on show now, you have Maria Carey also on show. So you see that the holographic technology is taking off. Now, holographic concepts in the future, the way it is envisioned today that you have musicians performing at different locations. You have the audience captured around the globe. And then you may have the avatars of musicians and participants projected in the same concept room, just as if everybody was in a live concert. So of course, you can see here, it is very challenging because this implies that you will now transfer avatar. You will now stream holograms. And intuitively, you do need a lot of bandwidth to transfer avatar. And also you have the delay issue. And of course, the media synchronization issue. Now, beyond holography, the scenario for a concert, we may think of a similar scenario for conferences, where we are all home, that we are all immersed in the same conference. Or more generally, we may think of the metaverse, which is a multi-dimensional, multi-sensorial environment with participants in different locations. They immerse and interact with each other in a shared environment. Okay. Let me cite the point that there is a lot of fuss around metaverse today, but nobody really knows if this will take off. Because the ambition is just too high. So this implies hologram, streaming, tactile, internet, and so on. And it is interesting also to mention that Meta has shut down this metaverse branch. Okay, so this brings me to the outline. I will introduce volumetric media delivery, introduce network computing, then the principles for applying in-network computing to volumetric media delivery, a case study, and then I will conclude by the research direction. Volumetric media are going to be a thing. I will define it more formally. So this goes far beyond 3D representation of objects. We are talking of 6 degrees of freedom. So if we take traditional video, or the user has a passive mode, we just watch the video. If we take 360 degree video, we have some level of immersion in the sense that the user can turn the of the head and can set the view. Now, if we move to this degree of freedom, and then the user may not only move head, but may change position in this. So as you might imagine, I mean, this is definitely a lot of data. And that's why this is called volumetric. I will illustrate this on the next slide. Yeah, before the illustration. Volumetric media delivery, this implies that you capture hologram, you represent it, you encode it, you eventually transcode it, decode it, and then you render it. And then we see here the requirements on the network. Ultra high bandwidth. Just an illustration from one of the references I have. They go up to 2 gigabits of data per second in the context of 30 frames per second. And we also do need ultra low latency. So it may be as stringent as 1 millisecond country latency. The consensus today is that the network we have today cannot offer that bandwidth and cannot offer that ultra low latency. 5G, 6G may help for the ultra low latency, but we are not yet there. So that's why we do need techniques in order to reduce the bandwidth and also in order to reduce the delay. Okay. One known technique is, of course, edge computing. But we will see later in the presentation that edge computing cannot do it. So the idea we are putting forward now is to use in-network computing. And we have shown in our use case that with network computing, we can potentially have better results than edge computing, meaning what can be used up to now. This to illustrate the bandwidth requirement. If we start from HT and we go to hologram, one cloud hologram or live field hologram. So it is clear, no network today can offer that bandwidth. Now let us talk of network computing. The definition is quite clear. is that you break somehow the basic internet principles by computing inside the network as an alternative to computing on servers outside network. And I mean, it is clear that one of the fundamental principles behind internet is to compute outside network. Interestingly enough, like many things, it is not new. It is actually the active network from the 90s. I will explain very briefly the principles of active networks. I explain also somehow why it did not, there was no compelling use case, and besides that, the technology was not yet mature. Now we have a resurgence due to recent technical developments, especially SDN and data plane programmability. Sure, I mean, to break internet basic principles, you do need some strong motivation. In the 90s, there were few use cases somehow compelling, but not really that compelling. Network management, essential, active network management. They say that you can get the notification in each node and handle the notification there, instead of sending the notification to a distant server with SNMP or CD. Okay. But what has happened later on is that it came out that with in-network computing, you can also tackle the high bandwidth issue and also the low delay issue. And these motivations are more general and more compelling somehow than the isolated case of active network. How does this work? In the 90s, yes, there were some programmable switches, but okay, SDN was not there or was not mature. But one idea of doing at that stage, and which now is rather close to what we do with programmable data plane capsules, is the concept of mobile agent, and that you inject code in the network and the node executes the code. That's the way it was done before. And this is a bit close to the programmable data plane with SDN before, is that when the data goes to the data plane, you have the possibility to execute a piece of code on it. So the way network computing is done today is through programmable data plane, essentially. And we have some languages like P4, which allow us to program the data plane. I mean, this goes far beyond the control plane programming that we are used to. P4 has some basic constructs. It's not very rich as programming language. On the other hand, it offers the possibility of Esther, meaning that you can put any piece of code you wish on the switch, and when you trigger the P4 program, the P4 program will execute that piece of code, which is programming Python or C++. But okay, there are some limitations, and I will mention them here. Sure that we have limited processing capability on there's no doubt about that. So this brings the key issue of what to compute inside the network and what to compute outside the network, meaning on them. P4 is not that expressive. We do have the possibility of complex implementation with STEM, but the problem with STEM is that there we lose one key issue. We lose one key feature, which is interoperability. With P4, you write the program on P4, you are sure that you can execute it on any P4 enabled switch. Now, if you introduce Esther, and the way to program Esther vary from switch to switch. So you lose the interoperability feature. There are also some problems concerning the general deployment mechanism. Okay, now let me move to the general principle for using in-network computing for volumetric media. Let us take the general framework, which is now reaching to continuum cloud edge. Okay. So the way it is done today, if you remember, I have mentioned the components. Yes, like encoding, transcoding, decoding, and rendering. These are the components. So if you wish to stream holograms, you shoot the hologram, where the hologram will go through these components. Right? To be encoded, so you do need a piece of software to encode the component. It may be a VMF, and as we are putting forward now, it may also be a piece of P4 code. So you have these components. So the implementation today, they place these components in the cloud or at the edge. This is the most advanced implementation we have together. So sure, depending on where you place these components, and delay will vary. And also network. If you put the whole thing in the cloud, sure that you have very long delay and so on. So in a traditional implementation, and this might be implemented as DNS, containers, and so on. Now, if we bring in network computing in the picture. What we propose is to implement some of these components as a network component and run them in the network. As simple as just to get better results in terms of delay and also for reducing network load. Sure, if we take transcoding, and when you transcode, you go to different formats, and you can reduce network load. So if you do it inside the network, it will be better that you do it at the receiver end. Okay. Now, when we talk of network here, unfortunately, I don't have a picture, but essentially you have a sender. Okay. So it is a server shooting out the hologram, and then you have a set of receivers. Okay. Now, if you take the senders to be connected, we have an access network. And in this access network, we have routers. So we have a possibility to put components on these routers if they are in network computing enabled. Now, if we go to the core network, it is the same thing. We have a set of routers, and the edges also are connected to routers. So we have a possibility to put components on any of these routers. So to summarize this before moving to the case study, is that so far to tackle the delay issue and also the network load issue, what has been used so far is edge computing. We know that edge computing can help in improving delay. That's actually why edge computing was born, because the cloud can be too far. And we also know that edge computing can help in order to reduce network load. And these were the two reasons for edge computing. However, it is clear that with edge computing, it will be rather difficult to handle volumetric. There's the idea of trying something else, meaning in network computing. The case study it is a simplified holographic concept. Okay. So we assume that we have all performers in the same location. So that means that we have computers which will stream the hologram and then transfer the holograms to the participants, which will be in a remote location. So participants are in remote locations. Performers are on stage in the same location. So the issue is the network load, which will be generated by sending these holograms to participants in different locations, and also the delay. Okay. We are definitely at the beginning of this work. So what we did, we selected just one component, transcoder, as simple as that, to see by placing the transcoder inside the network router, or by placing it at the edges, or eventually by placing it at the sender or at the receiver, what we gain. And I think that the results were very promising because we did show that we gain a lot in terms of bandwidth and also a lot in terms of delay by making concrete measurements. So the only component that was implemented was the transcoder. But the transcoder is actually complex. It could not be implemented in P4. So it was implemented as an external. So that the scope and the architecture. We are here in the context of 5G, CG, or what is called the next generation network. So what does this mean? This means that we have slices, okay? And a slice, you can see that a virtual network for specific category of application. So on the same next generation network, you might have a slice for holographic streaming, and that slice should be able to accommodate volumetric data. And beside that, you might have just slices, very simple slices, which will accommodate conference. So a slice accommodates the requirements of a specific application. So as you see here, we have an holographic application provider, which will request a slice, meaning a virtual network, in order to deploy holographic streaming. Okay. So that the application provider, now when you get that request, what do you do with it? Because at some stage you will need to map this request on the actual network, on the real network. And that's what we call slice embedding. So we have the slice embedding layer here. In order to embed the slice, you have to know what are the resources you have inside your network. So that's why we have something here called the resource utilization monitor, which will go down, get the resources that are available in the network. So by taking these resources as input, and by taking the requirements of the application, then you should be able to know where you can run each component. Okay, we have an adapter here because we assume that we have an heterogeneous environment. So we do have SDN, and we have a data plane layer, which is programmed with P4. And this is the implementation. So we have implemented a simplified embedded layer, a simplified application layer, we have an SDN controller, and we have the P4 enabled switches, or the in-network component enabled switches. As you see here, we have the holographic concept. There are several computers which will prepare the hologram and streaming. We have the holographic streaming server. And then we have the remote participant. The beauty here is that it will not be like watching a movie or just watching a video. I feel that's the beauty. To just be as if you are completely immersed, as if you were in the concept of it.
How remote the hosts are? How far are they?
This is a
Three switches? 3 switches far or more?
in our simulation, maybe of as we can, because one. Yeah.
No, how far are the?
Yeah, in the simulation, how far
Yeah, we go to up to 5 switches.
Okay,
in the simulation?
so it's an access network. We don't go through routers.
These are programmable switches.
Okay,
Yeah,
They can
yeah.
be also 4.
okay,
I mean, it doesn't matter the number of switches.
because we have delay constraints.
Yes, the impact will be on the back selection.
Okay. Mhm.
We have some measurements here, and you can see them in the paper.
Mm.
But for sure, I think that we have shown clearly there that the idea of using in-network computing to reduce network load and to reduce delay for holographic streaming is not far-fetched. Without hosting, I think that we can claim that we were the first team to make concrete measurement for this and to put the idea on. Our future research direction, and we are still working in the area. This can be considered somehow as a greenfield. There is a lot that can be done. I will talk now a bit about the architectures. I know that these days, I mean, the passion is more to design algorithms and to simulate them, but we still build reality in our prototype. Yeah. So for sure that one thing is to have an architecture, a general architecture in which we have cloud, and we have edge, and we have in-network computing enabled hardware. To prototype this and show that this is feasible. I mean, yeah. With software modules, interfaces, and so on. Linked to the architectures more concerning the components. We know this with VNF and other components. A challenge is to describe the component. You might go just from XML, you might go with ontologies and so forth. So one thing we wish to do there also is to describe the components, including the traditional and the network enable components that should run on routers. On the algorithm side, of course, that a challenge is the component placement. There is a lot of work on VNF placement. But okay, VNF are placed in an environment with virtual machines and so on. But we wish not to place VNF, but also to place the network component. The problem is different because I mean to place the network component, for instance, if you are dealing with a component that you have implemented as an extern, you will have to place the extern first. And the way you will place the extern will vary from switch to switch. When the extern is placed, then you will run your P4 program at some stage to enable the extern. So component placement and management. And of course, you place, but you need to embed. Of course, you also do need a lot of sophisticated algorithms to embed. So this depends on the dynamic resources you have in the network. I think this brings me to the end of my presentation. Thanks for your attention. Question, comments?
Thank you.
Yes, there is a question.
I think of the presentation. So I was wondering what does strong coding consist of, like, and why we don't do like if we do it on the switcher or on the router, is it like it's something that's redundant or
No, sure, yeah. Transcoding, the origin of transcoding somehow is that cellular phones do not have the same capacity in terms of processing and so on. So when we have video streaming, we have the video which is encoded in a given way. So at some stage, we transcode the video. We may lower down the quality in order to make it viewable on your cell phone. Okay? So you start with something and you lower the quality for specific cell phone. Okay. From the moment you lower the quality, the data is left big. Correct? So sure, if you do this at the receiver end, that means that you transport in the network the volumetric data. You transport it to your cell phone, and then at your cell phone, you transcode in order to see it. Okay. However, if you put the transcoder in the network, that means that you transcode inside the network for different users, and the data that goes in the network is less.
thank you for the explanation. So basically, the server, if it, the video or the data at high quality.
Yeah, in the best quality,
The best
of course.
quality. So basically, if, I am on my cell phone and someone else is on the same switch on his computer. So basically, we don't have the same quality. The data should be more have more quality for his computer. Like the switch now is delegated to our devices.
Okay, so let's say that the principle is that you should be able to view the video. Okay, and if I send that big video to your cell phone, you cannot view it. Okay? So that's why for your cell phone, the video will be transcoded to make it viewable on your cell phone. On the other hand, the participant who has a very powerful device should be able to see the video at the best quality. Okay, so what the server sends out is the best and highest quality. But depending on the participant, this quality might need to go down in order to make the video viewable.
What I was asking about is the protocol that enable us, for me, for example, for my device, I would like half the quality, and for another device, I like 1/3 of the quality. So basically, is this like the switch, like take it half,
Okay.
reduce to half the quality, and then send it to me and send it to me? Or
Okay, so
Probably the question is how the in-network components will know the requirement of the receiver end.
yes, of course.
Yeah.
I did not show. Yeah, you have a point there. So the assumption here is that we know the quality. I mean, we know what your cell phone could receive.
Yeah.
And in a cellular context, we know it by the base station or by edge computing. So that means that you do not select it. We know. Okay. So that information which is in the cellular network, we assume that by some mechanism, we can make the network know. So that's the assumption.
It's probably linked to that.
Sure.
Why don't do it in the sender? Like you could transcode in
Yes.
format and just
Yeah, it is an excellent question. The point here is that at the sender side, it is just impossible for you to know in advance all the different cell phones which will connect. You see my point?
but you could select like a possible configuration spec.
That's correct. So actually the way it is done with adaptive streaming is that definitely at the sender side, you do it for maybe 10 different types or 20 different types in adaptive streaming. But even if you do that, in most environments, you will have other types of cell phones. It is definitely a kind of infinite range of what we do. Yeah, but it is a good point. Yeah. And it is done with adaptive streaming. Yes.
Okay, so in fact, it's some the next step of the question regarding Dash. So I think you are talking about
Yes.
Dash. So I don't know if you have in mind to see how your networking scheme compared against Dash. Because in Dash, so you already set many video qualities, and depending of the context of the user, you just pick the right quality and send it. So I like maybe this one because it's some centralized, it's make perform better.
I'm not sure I see your point. The in-network computing, as we see it as a complement to HTTP dash.
It's about user-centric.
Yes, right. Yeah, is a complement. Now because the big point here is that with HTTP dash, you have a limited set of transcoding, and indeed, if you could have all the possible transcoding you wish to do, then I do not think that you need to do it in the network. You will just do it at the server side. This is clear. That is answer your question.
Yeah. And what about the quality of experience? Is it improved using networking?
The quality of experience, if you see it from delay perspective,
Delay, jitter, maybe also.
Yeah,
To be
delay and
uh,
jitter,
yes,
delay and jitter.
jitter, yes, yeah, because we also made some measurements.
Yeah, but these are quality of service parameters.
Yeah.
But-
On quality of experience that we didn't. And there is no formal way to describe quality of experience, but we conclude that if the quality of experience that could never be quality of, if we reduce the delay, for example, and the jitter, that could have an impact on quality of experience.
And since the feedback is faster, quality of experience is supposed to improve.
Yeah, but the quality of images will be lowered. But the quality of
Probably.
experience will be lowered.
Quality
too.
of service.
Yes, I mean the quality of image, it will lower for the phones which cannot support high quality, not for the other phones.
But nowadays, most of cell phones we have are much powerful compared to switches.
It,
So,
yeah, it may be the case, but it depends also on where you are in this world.
Yeah.
Yeah. But I mean, one thing I wish to stress here is that the holographic streaming and even metaverse, I mean, they are just used cases for that's the key thing. What we are researching here is in network computing for high bandwidth and low delay compared to edge, because I mean, edge is what have been proposed so far.
Yeah, the benchmark is
Yes, right, because it is the best we have now in the literature. If we talk in terms of component placement, I must stress also that you have also other things tackling the problem from cross-layer design
Mm.
perspective. You still use HTTP dash, but you see if you can get information from the physical layer and so on in order to have better. But I mean, if we talk of microservices or component placement, then for sure, edge seems to be the benchmark now.
Any questions from Zoom? So what is your feedback about before?
Yes, there seems to be a big issue with P4 now.
Hmm.
Okay, but
It's what I know, yeah. So
I will answer the question in two steps. The first step is that there is a consensus today that we need to program data plane.
mhm,
Today, P4 seems to be the most popular, most advanced language.
mhm,
That's the first step. The second step is that due to the fact that Intel has purchased Belfort, they are planning to shut down the production of P4
mm.
chips, then I do not know what will happen. That's my point. If P4 disappear, it will certainly be replaced by another language to program data.
Yeah. So do we see another language that is emerging?
It's something I have to look into.
Okay.
Yeah,
I think they are only stopping the production of Tokuno keys, which is not the first, the Tokuno 1 and 2 will continue.
Okay. You seem to be
Yeah, this will be the next step.
okay. So because anyhow, it will be difficult for Intel to shut it down because this has gained popularity.
yeah.
P4, I mean, you have many SDN switches which are
Okay.
P4 enabled
Mm.
and others. So I strongly believe in data plane.
Program.
But I believe there are other languages than people, but people is the more, is
One, two, or three, four.
the most used. Yeah. But yeah, as Roch said, also people have this problem of expressiveness. You cannot implement classical things we are used to do in other languages. Even
Yeah.
for loop or
Again,
I can't give explanation about this. Intel just stopping the production of Tokuno 3. Tokuno 1 and 2 will continue, and give you explanation there.
Okay.
And the community working on this programmability of the devices. So this is not something that we can stop it and we reach the conclusion that it's not working. Maybe there is some reason why Intel just stopping the production of Tokuno systems.
Yes, that is essentially.
Konta, are you familiar with before?
no,
No.
I will look into explaining.
Zakaria.
It's one for
Yeah, Zakaria used to use it.
Before.
Yeah, he used to complain. He used to complain all the time about before.
I guess in this context,
Yeah,
that's what otherwise, I think.
no, it's because the people in itself is a dispersed language.
Because you have limited access to the physical resources on the switch.
No, the
Also.
people wasn't meant to be used for other things than data plane product.
that's correct.
Yeah. But how we do it now is we call, for example, for cross-coding, we are calling extend. People can allow you to call extend.
Okay, so then you can do that.
Yeah, you can call extend. So for example, the cross-coding was in a sea of, for example, you can call it, but this takes time. What we want is to
It is switching to the historical.
exactly, yeah.
Yes, it takes time, but beyond that, is that if you call and extend, if you run it on a Cisco switch, you will not be able to run it on another switch. So the interoperability is lost there.
Yes.
Mm.
With Esther.
Yeah, this is.
Yeah, so this is the issue.
This is a big challenge to find a good programming language to do the in-network computing, which is right.
Now, I do not know if there are plans to extend people. Mohammed, you know something about that? No, I don't know.
In their workshop, people propose some different ideas.
Okay.
I saw one paper they proposed how we can get the loop in the people. And I think what, if I remember, one of the constraints of implementing the transcoder in the people was loop.
Yeah.
So people are proposing how we can handle the constraints.
Good. Any more questions? Okay, thank you
Thank
very
you,
much,
Roch.
Roch.